Hello, viewers. Hello, students. And hello, everybody who comes to this channel and views what I write and what I explain. This is part two of the chapter on solutions for CVSC and IAC courses. Colligative properties of solutions are a fascinating aspect of solutions. They are a group of properties that depend on the concentration of solute particles in a solution rather than identity of those particles themselves or the nature of them. In simple terms, how much stuff you dissolve, that is the concentration, affects these properties, not what kind of stuff it is. So kind doesn't matter. How much it is, that matters. Here are some key points about colligative properties. The name is the game. Colligative comes from the Latin word colligare, meaning to bind together. But here, nothing gets bound together, reflecting the link between these properties and number of solute particles. So that is bound together. The number of solute particles and how it affects the colligative properties of solution. What matters is the crowd. Colligative properties are influenced by total number of solute particles, regardless of their size. Very important. Size doesn't matter. A big or small molecule doesn't matter. Chemical nature doesn't matter. Whether it is sulfate, carbonate, phosphate, bicarbonate, bisulfate, bisulfite, doesn't matter. How many they are does. For instance, a teaspoon of sugar, many small molecules, will have a similar effect as a teaspoon of table salt, fewer but larger molecules on a colligative property, assuming the same concentration. That is, number in a given volume must be same. Real versus ideal solutions. The concept of colligative properties is most accurate for ideal solutions. These are hypothetical solutions. So that means, you see, they exist only on paper. They do not exist in reality. So these are hypothetical solutions where solute-solvent interactions are negligible or are non-existent. And particles behave like perfect spheres. Real solutions deviate slightly, especially at high concentrations. However, for dilute solutions, the colligative property effects are still a good approximation. That means the values obtained when these colligative properties are measured may be approximately what we get in calculation. The four colligative properties are as follows. The lowering of vapor pressure. Adding a solute lowers the vapor pressure of the solution compared to the pure solvent. Imagine fewer solvent molecules are able to escape to the vapor phase due to crowding by solute particles. Raoult's law helps quantify this effect. We will see what is Raoult's law later. Elevation in boiling point is one of the colligative properties out of the four that we are going to study. So first, we are going to study each of them in quality before we see how they can be quantified using equation and different variables. Boiling point elevation, as mentioned earlier, this is the increase in boiling point of a solution compared to the pure solvent. When a non-volatile solute is added to a solvent, it disrupts the orderly arrangement of solvent molecules at the surface, hindering their escape into the vapor phase. So they come in between, and the point from where the solvent molecule would have escaped, these non-volatile solute particles take their place. so fewer particles go into the empty space above. This requires a higher temperature, boiling point, for the solution to boil and achieve the vapor pressure as pure solvent. The greater the concentration of solute particles in the solution, that's more crowding, the more significant the disruption of solvent molecules on the surface, and this translates to a larger elevation in boiling point. The more it is lowered, the more it is going to be elevated, or the more heat it will require, or higher temperature it will require to reach the same vapor pressure at which the solution will start boiling. Remember that boiling point is a function of superincumbent pressure, that is pressure acting on the liquid surface from top. So when the vapor pressure of liquid equals the superincumbent pressure, the liquid starts boiling. Since the vapor pressure is lowered by addition of non-volatile solute particles, as the surface gets disrupted and fewer molecules escape into the space above, more heat has to be applied, more temperature has to be raised to equal this lower vapor pressure and bring it to the superincumbent pressure level, so that the liquid molecules start escaping from the surface. Depression in freezing point. A pure solvent has a specific freezing point, which is the temperature at which the liquid and solid phases coexist in equilibrium. Water freezes into ice at 0 degrees centigrade. Ice melts into water at 0 degrees centigrade. So at 0 degrees centigrade, water and ice coexist. Adding solute, when a non-volatile solute is dissolved in the solvent, it disrupts the orderly arrangement of solvent molecules at the surface, as we have seen earlier. This makes it harder for the remaining solvent molecules to form the ordered structure required for solidification. Very important line, very important line. Remaining solvent molecules to form the ordered structure required for solidification. Lowering the or lower freezing point, consequently the solution's freezing point gets depressed. In simple terms, the solution needs to be cooled to a lower temperature compared to the pure solvent for it to freeze. The extent of depression, the amount by which the freezing point is lowered, that is del Tf, change in temperature of freezing, depends on the molality of the solute, moles of solute per kilogram of solvent, and solvent specific constant called molar freezing point depression constant, Kf. The relationship is expressed by the equation del Tf equals Kf m, that is Kf into m. Osmotic pressure. Osmotic pressure is intimately connected with the process of osmosis, which is the spontaneous movement of solvent, usually water, across a semi-permeable membrane or selectively permeable membrane from a low solute concentration region, that is hypotonic solution, to high solute concentration region, hypertonic solution. Here is a breakdown of osmotic pressure. Definition: the osmotic pressure is the minimum external pressure required to prevent the inward flow of pure solvent across a semi-permeable membrane separating a solution from pure solvent. So it has to be applied on the surface of solution, because the molecules of solvent will flow through the membrane into the solution part. Then the factors affecting osmotic pressure is the solute concentration and temperature. The greater the concentration of solute particles in solution compared to the pure solvent, the higher is the osmotic pressure, the higher is the pull with which it will attract the solvent molecules coming across the semipermeable membrane. Temperature. Osmotic pressure increases with temperature, similar to the behavior of ideal gases that we have learned in grade 11.